Hi, this is Thanga Rajan. Today we are going to see the deflection of beams using Macaulay's method. Macaulay's method is one of the method for finding the slope and deflection, and it is the easiest way to see how Macaulay's method has to be used for finding the slope, for writing the slope and deflection equation. So Macaulay's method, it is one of the method for finding the slope and deflection of a beam. It is an easy method which enables us to write a single equation. Suppose if a beam has multiple load, we can able to write the single moment equation. We can able to write a single moment equation easily over the entire length of the beam. In this method, the bending moment should be calculated from the section X. Actually, for example, let us consider an example of a beam AB shown in the figure. It consists of one point load, one moment, and one UDL load. So let me name these points as D, E, and F. Okay. So point load W is acting at a distance of A from the left support. M is acting at the point E, which is at a distance of B from the left support, and UDL is acting between the points F and B, which is at a distance of C from the left support. In this method, the bending moment should be calculated for the section X, which has to be marked as the last portion. This is very important. Last portion of the beam from the left support. Here, this beam consists of the portion AD. AD is one portion. DE is another portion. EF is another portion. FB is another portion. Totally, this beam consists of 4 portions, 1, 2, 3 and 4, or it has 4 divisions, 1, 2, 3, 4, right? So whatever the beam may be given in the problem, it has to be split into different portions by assigning the name at the point of application of the load on the beam. Writing moment equation. Let us see how to write the moment equation using the Macaulay's method. Here I have given 4 examples. One is for writing the equation for a reaction force. Another one is for the UDL load, UDL load, and third one is for a point load, and fourth one is how to write an equation for a moment. In all the cases, we have considered the section. In this example, I have marked the section here just for an example. Actually, in Macaulay's method, we need to write the value at here. So this is we should. So here assume there is no load. So here you have only one portion AB, right? So when you are writing the moment equation, in this first example, here you have a section. The section is from a distance of X from A. You have to appropriately choose the sign. While writing this Macaulay's method, here I have assumed the clockwise moment as positive and anti-clockwise moment as negative. Considering this line, this reaction force RA, this is RA, this is RA. So considering this force RA, this RA creates a clockwise moment. Hence M equal to RA into X. Here clockwise moment is positive. Clockwise moment is positive. Clockwise moment is positive. Hence choose MA equal to RA into X. This is a positive one. And second one is the UDL load. When you are writing the UDL load, here the section is marked in the last portion. So when you have a UDL, the UDL CB between the CB, we all know that for UDL load, moment equal to W into X square divided by 2. Here, this is the portion X minus A. This is X minus A. So when you write the equation for an UDL load, M equal to Wx square by 2, here X minus A is the distance. So W into X minus A the whole square divided by 2. So for all UDL, when you have a section X section across the portion CB which has the UDL load, M equal to W into X minus A the whole square. Suppose if it is B, here X minus B the whole square. W into X minus A the whole square divided by 2. Next one is the sign. Here this W load creates a downward direction force. With respect to this section, this downward direction force creates an anti-clockwise moment. Hence, we use minus W into X minus A the whole square divided by 2. Now, if we have a point load, M equal to, again, this point load is a anti-clockwise moment. So, use minus sign here. When you have a point load, and here also you have the distance. So this is X minus A. So M equal to minus W into X minus A. W into X, instead of X, X minus A whole power 1. If it is a UDL means X square by 2. If it is a point load means X minus A divided X minus A whole power 1. And in the fourth case, the distance, here no need to calculate the distance. You straight away write as moment as M into X minus A the whole square, because in moment already it is in kilonewton meter. So already the distance is calculated. Hence I use the power 0. So M equal to, if this is a clockwise moment, here it is a clockwise moment. Hence M equal to M into X minus A the whole square. Right? The term X minus A, while you are using or integrating, you should consider these X minus A as a whole, not as a single. Now before you write the equation, there are certain things which you need to remember. So always take extreme left of the beam as origin and assume clockwise moment as positive and anti-clockwise moment as negative. This we have already discussed in the slide. The constant of integration should be added in the first portion only. When you have a beam, you have 3 or 4 portions. So the constant of integration should be added only in the first portion. The constant of integration should be obtained by applying the boundary condition. We have already discussed the boundary condition. For a simply supported beam, the deflection is 0 at the supports. For a cantilever beam, the deflection and slope is 0 at the fixed end. Next point, fourth point. Here, the unit of moment is kilonewton meter. When you integrate this kilonewton meter, that is integrate M into dx, will give kilonewton meter square. The unit for the slope is, that is EI into d square y by dx square. So here M equal to E I into d square y divided by dx square. So substitute m equal to ei into d square y by dx square into dx. This ei d square y by dx square, when I am integrating one time, I am getting the slope ei dy by dx. That unit is kilonewton meter square. When you integrate one more time, you will get ei into y. So here I get ei into y. So ei into y unit is kilonewton meter square. So these are all the things which we need to remember before writing equation. And also for finding the maximum deflection, the maximum deflection is obtained when the slope is 0. This is very important. To find the maximum deflection, equate the slope at every portion to 0 one by one till the slope becomes 0 and determine the value of x. And last point, this is a very important point. Very important point. If there is a UDL which does not extend up to, suppose consider a beam AB. So when I draw here only I draw the section. So when I draw the section, and if the UDL is in the portion CD, you need to extend this UDL by adding the portion CD and subtracting the portion DB. So you have to add and subtract appropriately. When you have the portion like this, you have to add the UDL and subtract the UDL, and then you should write the equation. This is another important thing which you need to remember. And this is an example. Here I have given an example. Here I have a beam. A, B is a beam. You have a point load W at the point D, M at the point E, and FB has a UDL. So we all know EI equal to d square y by dx square, that is equal to m. Now you need to write the equation. This EI into d square y by dx square. So you have 4 compartments. So this is 1, this is 2, this is 3, and this one is 4. You have 4 compartments. So similar to here, 1, 2, 3, and then 4. FB is 4. Totally you have 4 compartments, 1, 2, 3 and 4. So I have marked the distance in the, I have drawn the x value in the last portion FB, 4th portion. So first let me have the reaction force Rx. So Rx, we have already seen that Rx should be multiplied by x. Rx creates a clockwise couple, hence this is positive. And second portion DE. So DE has a load W. Just now we have seen W into x minus A. So this is the distance. So this is the distance. So x minus A power 1. X power A power 1. W into x minus A power 1 minus. And this is a clockwise couple. This is in the second compartment. So now I am moving to the third compartment. From here I am finding I have 2 forces. So Rx I have already written. W I have already written. Now I have to include the moment M. So M equal to x minus B. So the distance up to the point E is B. So x minus B the whole power 0. So this moment is a clockwise moment. Hence I am using a positive sign here. And in the last portion we have the UDL. So UDL W into x square by 2. So W2 into x minus c. So this is x minus c. So this is x minus c. So W2 into x minus c the whole square divided by 2. So which is the Macaulay's moment equation. Macaulay's moment equation. Macaulay's moment equation. Once when you write this Macaulay's moment equation, it is easy for us to find the slope and deflection. So when you integrate this equation one time, you get EI into dy by dx. RA, it is a constant value. When you integrate x square by 2, and the constant integration constant should be added only in the first portion. Similarly, second portion, w is kept as constant, and x minus a should be integrated as a whole, x minus a the whole square divided by 2, and third one, x minus b should be integrated as a whole, so x minus b whole power 1 divided by 1, so m into x minus b whole power 1, and the last part w2 by 2 already there, and x minus c the whole square, when you integrate x minus c the whole square, x minus c whole cube divided by 3. So now you have the equation for slope. Now when you integrate the slope equation one more time, you get the deflection. EI into y equal to RA into, so 2 already here. So when you integrate x square, x cube divided by 3 plus C1x plus C2. So again this integrating constant should be added only in the first portion. So minus w by 2 and x minus a the whole square, when you integrate x minus a whole cube divided by 3. So similarly here m into x minus b the whole square by 2 third portion, and w2 into x minus c the whole power 4 divided by 2 into 3 already there. So x cube, when you integrate x power 4 divided by 4. So till the end you must follow the partition line. This is the partition line of different portions 1, 2, 3, 4. Till the end you should follow here. The integrating constant, the integration constant C1 and C2 should be determined by applying the boundary condition appropriately. Thank you.